All right, so I will talk to you about runtime support for programming multi-GPU systems. So some motivation first to set the scene. When would you need to go beyond the scale of a single GPU? Simply, you need to address a problem that needs more than can be done on one GPU. So, for example, having a lot of computation that can be parallelized, or processing a large amount of data that would benefit from having more than one GPU's worth of memory bandwidth. So that should be uncontroversial. The next should also be uncontroversial, that multi-GPU programming is hard. And why is it hard? Because besides all of the normal issues with programming a single GPU, now you have to deal with partitioning the computation, partitioning the data according to what the computation needs, handling the data movement, minimizing the amount of communication, because that's what's going to eat up all of your gains from going to GPU. And you need to synchronize, coordinate the execution between the different GPUs. So a whole other layer of complication that makes even a simple implementation difficult, let alone a performant one. So you might have seen this slide in the previous talk. So this one kind of unscientifically places different solutions to this problem on a grid. So the vertical axis is meant to present productivity, and the horizontal axis like domain specificity. Don't interpret the specific locations very closely. They're kind of just there for exposition. I just tend to categorize these solutions into three areas, conveniently aligned with the three talks in this session. Mads already talked about the first class of solutions that are meant to be productive, and if your solution fits within their space, then that's what you should use. And they can give you expose you to the GPU pretty efficiently. This talk is going to go one layer deeper and talk about different ways that you would build such systems. So what is the middleware or runtime support that's needed to build such solutions? So that's this talk. And then on the domain-specific, I guess, part of the spectrum are the libraries like Nickel and MPI that the next talk in this series is going to address. These are APIs that would be used to build up these higher level abstractions, and unless you need to, you may not need to use them yourself. They would be what a library would use to build up its own abstractions. So there are different ways to build up a multi-GPU runtime environment, especially when we're talking about this solution that's meant to be kind of a middle ground between the CUDA libraries and the high-level abstractions. I'm going to be focusing on the task-based paradigm, where because we believe that's one of the simpler programming models to expose you to multi-GPU execution, simply because it keeps the sequential semantics of the model that most programmers are already aware of, and they can reason about and debug. And instead of having instead of having functions, you have tasks, which are the fundamental unit of execution. They're operating on distributed collections, and you emit these things, and it's the runtime's job to infer the dependencies, infer the required scheduling and communication data transfers. But as far as the user is concerned, I'm just emitting a sequence of tasks, and the runtime itself is responsible for making sure that if there's a data dependence, the second task will only start after the first one is finished. So compare that with writing directly to MPI or like an actor model or something like that, where you need to explicitly write what each worker is doing. In this model, you're operating at the level of a whole logical collection. And there's different ways. To build up such a system. So this talk will be talking specifically about Legate and Dask, and I have kind of an informal comparison on this slide. The main things that I'm going to be talking about are the different approaches to data abstractions that the two runtimes take. So how informed is the runtime about the placement of the data, and how much how clear is it to the runtime what its piece of data is representing? I'll give more details later, and then some notions about mutability, multiple partitions, and how the task graph is constructed explicitly or implicitly. Yeah, you might have heard Fred introduce me as a member of the Legate team, so that might inform my biases, so maybe keep that in mind. I have prepared some examples that I'll be showing throughout the presentation. They are available on this URL if you can get on the internet on the convention Wi-Fi. They'll just be simple examples that are only meant to work on a 2 GPU machine, and they're not how you should do things most of the time. They're mostly for exposition. So if if your example fits one of the higher level libraries that Mads talked about, just use that. No reason to go to these lower level APIs yourself. So this is more about what the constructs are provided by the runtime itself that is used to build these libraries. And just as a teaser, here's what the Python side of these runtimes looks like. You can have a Python function, and you can annotate it with a decorator, and it says that this now becomes a unit of computation that I can send to a scheduler, and it will execute. There's some minor details, some fun details about what the execution model is. That are mostly not as relevant, but bear mentioning. So Legate, as the moment you launch something, it starts executing, whereas Dask builds up the entire graph, and then you have to ask it to execute. Just an interesting detail. But onto more interesting things. Data partitioning is the basis for how you're going to achieve parallelism. So in both the tasking runtimes, the way you achieve parallelism, or at least data parallel execution, is you create partitioning of the data, and you launch a series of tasks on that data, and then the runtime will realize that these are independent, these are processing independent of the data, so they can run concurrently. Now, this is the first area where the runtimes diverge. So on the left, I have Legate, and I don't have a pointer. You'll see that when you create this store, which is the distributed collection type for Legate, you don't specify a partitioning. The partition will actually be imposed by the task that's executing that data, executing on that data. So here we have a batched FFT implementation that by the time you enter the body of the task, you know that you are dealing with your local piece of the data. So that's what the output store, input store is like. It's my local piece of the data. And then within that, these are just pointers and strides. So they're buffers that I can operate on however I want. So in this case, I just create a CuPy view over them, and I execute a function to fill it out. So the runtime itself, in both cases, is agnostic to what happens inside the body of the task. Its job is just to give you the local piece and then let you execute on it. So in this case, what's important here is that the runtime will decide how this work is going to be parallelized, but there are constraints with what the correct ways are to parallelize. So in this case, we have constraints on the top. The first one says variance equals GPU, and it just says that this task must execute on the GPU because it's using device code. So it's calling CuPy, and then CuPy is executing on a device. So the runtime will know, okay, this is a GPU. This needs to run on the GPU. I need to put the data where the computation will find them, and so some sort of device accessible memory. Then the second constraint says that you can parallelize however you want, but you better make sure that the destination and source pieces align, so we're not reading the first half and writing the second half, reading the first half of the input and writing the second half of the output. And then the second one says that I don't, you can choose your partition according to whatever heuristics you're using, but you mustn't split the first dimension because I need to execute an FFT on that dimension, and I need each piece to have the complete dimension for that. But after that point, the task is essentially, we call it scale-free, so it's agnostic to the actual degree of parallelism. There's no requirement within the body of the task for a specific shape, and that allows the runtime some leeway into how it chooses to parallelize. On the Dask side of things, the user. So here I'm showing how you would initialize a Dask array, which is a collection of objects. It's a collection of futures that points to objects that will be computed and will be placed in a specific memory. So in this case, a Dask array is a collection. Because of my GPU, the machine had 2 GPUs. This would be 2 pieces, each of them represented by a CuPy array, and each placed on a separate GPU by default. So in this example, we would initialize the array as 2 CuPy chunks, and we would need on our control code, we would need to chunk it in such a way that whatever we want to do with it later, which is to run this FFT in a batched fashion, is safe. So we had to pick a chunk size that worked for that purpose. Like the first dimension of the shape aligns with the first dimension of the chunk. And then we would call this mapBlocks function, which takes each piece and executes the function on it. So each of these functions will take the local CuPy array, and they will perform the computation. So that's the notion of the basic partitioning in the systems. And here's where I'll dive a little bit more about what we've been talking about with the white box versus black box partitioning. So in Legate, the main difference is that the collections are built on top of global data abstractions that the runtime provides. So the runtime has an understanding for where essentially the user needs to tell the runtime how is the global view constructed and where does each piece fit within it. And then if the runtime has such visibility, it can reason about global data invariance. It can track the locations. It can keep various instances of the same data, possibly partitioned in different ways and placed on different memories. And you can even reason about, it can even support mutable collections. So there's a versioning system going on in the background that the runtime keeps the validity of different regions. It knows when a version is old and it's safe to be collected, and it can do that because the tasks, besides the scale-free property that I talked about, also need to define what the access modes are. So you need to say this task will read and write this input. So that constrains the partitioning choices, and that constrains or that informs the coherence mechanism of the runtime. In the case of Dask is more of a black box, takes more of a black box approach, so it allows you to build graphs of collections, graphs to represent collections, however you see fit. And those are, as far as the runtime knows, that is a collection of chunks. It's a collection of futures that backs different pieces. And the runtime has no inherent knowledge for where each chunk will fit. It's up to you as you build up your array container or whatever to keep track of which piece in that set of futures corresponds to what piece of the overall collection. Make sure that you know where that was last used. And if you need to create a new collection, essentially you create a new object with a new set of futures. Essentially, the collections in Dask are immutable for the most part. So you only get one partition. You don't get any coherence, any help with coherence, repartitioning, and such. And speaking of repartitioning, that's also one of the outcomes of having the white box versus black box data abstraction model. So often you would need to move data around to fit the needs of the next operation. And this is what normally a library like CuPy numeric or Dask array would do, like a higher collection library. So if you use those, then you don't need to worry about this problem. This is more about what the maintainer of these or the implementer of these libraries needs to do when it's time to do this. And here I'm showing a toy example of doing a row-wise to column-wise shuffle, but you can imagine more complicated patterns that would require a similar shuffle, like reduction tree or a stencil or a sparse matrix representation where it's even two arrays that need to be partitioned in compatible ways and repartitioned in compatible ways. So here on the left is the Legate version of this, where there is no explicit partitioning code. It's again the needs of the operation that will decide what the source partition is, what the destination partition is, and it's the runtime's job to figure out what the shuffle should look like. So in this case, I'm starting out with the first task, and I'm telling the runtime that the first dimension number 1 must not be partitioned. So this is a row-wise partitioning. So when I run this task, Legate will understand this constraint, and it will start out the data partition in a row-wise manner, and then this assertion will pass. In the next task, you pass the same store. Legate will try and read the constraints of the task and realize whether partitioning needs to happen, or maybe the previous partitioning is good enough. In this case, partitioning must happen. A repartitioning must happen. So it's on Legate to perform that intersection and move the pieces as is necessary between the GPUs. So move the missing data from one GPU to the other to make sure that the task sees the data in the way that it needs to. On the Dask side, this is what I've annotated how Dask array would do this. Caveat: I haven't actually read the Dask array implementation, but I'm pretty sure it would build up a graph like this. Maybe not this specific graph, but in this fashion. It would start. The data would start as essentially two futures representing the top and bottom half of the array. And then through a series of tasks or lambda functions that take the two pieces of the data. So it would split the top, it would split the bottom, and then shuffle them around to build a final representation of the two halves. So in this case, the runtime doesn't know that top L and bottom L are annotations that I put on the code. I'm the library writer. I'm keeping track of this information. The runtime wouldn't know that what each piece represents. So the runtime doesn't know which piece of the overall data is represented by each future. So it can't really check that you did this right and you moved correctly without screwing up the shuffle. But of course, someone wrote it for you. So if that is enough for you, then you can use that. And Dask array already has a lot of these conveniences built in, so you don't have to deal with that. Some of these other cases might get more complicated, and like the sparse matrices, stencils. Again, helps exist, but this is more about what the runtime can do for you versus you having to do for yourself. And then one more thing about data partitioning and the data partitioning support. Mixed CPU-GPU execution. It's inevitable, and in this case, the point of having a white box data abstraction is that besides knowing where the pieces of the data lie, there's also we're also keeping track of where each piece of the data lives, and a piece of the same array can at different points in the execution reside in either CPU or GPU memory. And it's in the case of Legate, it's the runtime's responsibility to move the data depending on where it's needed and the constraints of the task. So in this case, I have a task initialize which has been constrained to run on the CPU, and the runtime will know this information. It will know that the data must be instantiated in the host accessible memory. The next task uses cuPy-numeric, which can handle data in both locations, and it has kernels or task definitions for both. But in this case, I'm constraining the execution to GPU, so the data will have to move, or Legate will have to emit the copy and invalidate the previous, the previous version if necessary. In the case of Dask, again, as far as the runtime is concerned, a collection is a series of futures. So each of the futures could reside in CPU or GPU memory, and it all depends on where the task runs, where that node in the task graph executes. So it's more of the library's responsibility on at the task definitions level to move the data where it's going to be needed. So in this case, I'm starting out with an array, with a default task array without changing the backend. So we'll start it on RAM. And then the first thing I do is that I execute cuPy as array on each of the blocks. So this would mean that each of the blocks locally to that GPU will transition the data to device memory. And it's the user who is initiating that transfer. Now, the Dask CUDA that NVIDIA provides, the extensions to Dask that NVIDIA provides will make sure that this transfer happens efficiently. It will understand that if there is a shuffle or a device or a memory move needed to be performed, then that uses the accelerated network. But that's more of a bottom-up decision at the level of the task definitions, instead of being at the level of the global runtime. So I'll talk a little bit more now about the interoperability question and how the different runtimes address it. So first is how do libraries built on top of the same framework compose with one another? So in this case, I'm showing an example of cuPy-numeric and Legate data frame communicating on the Legate side, and the more or less equivalent libraries, Dask data frame and Dask array, interoperating on the Dask side. So on the Legate side, both of these libraries are built on top of the logical array and logical store abstractions that Legate provides, and because they are both using the same backend, Legate, the runtime knows how each one is partitioning their data, and it knows, for example, if one of them provides only a row-based partitioning, that whenever data transfers between the two, the data needs to be reshuffled. So the point here is that the libraries don't need to know about each other, and because the data is the data abstraction is shared, you can even have mutable access to the same data through different interfaces. Even if data needs to be repartitioned, the runtime will make sure that the latest version appears in whatever partition is necessary. On the Dask side, the point is that Dask data frame and Dask array can interoperate. But the point is that Dask data frame in this case knows how Dask array interprets its collection of futures. It knows what Dask array means when it keeps a sequence of future objects, and it knows how it can go from like a tile partition to a row partition if that's what it needs. So the two can interoperate, but it's the one library's job to figure out the partitioning and build a task graph to convert from one to the other. So it's the composability story here that's different. In interoperability with collective communication libraries is something that is likely to come up if you're trying to implement certain kinds of algorithms that require all-to-all communication or fine-grained overlap between computation and communication. And here there is some support that the runtime could offer to make that interop easier. In Legate, on the Legate side, there is a mechanism where if you define that your function takes a communicator, in this case nickel, it will provide the communicators for you, and it will cache them when using the same devices. It can give you the same set of communicators, so there's no overhead of creating a communicator at the task entry every time. And it will manage the streams that are provided to the tasks so that the CUDA effects can be tied into the task completion. So here I've written to the C++ interface because some of these, the nickel API was not available, or I wasn't aware of a Python front end to it. So I wrote this example in the C++ Legate interface. So that's part of why the verbosity is here. But you can see that this, you see in the full example that this task is initialized on an array, and then that array gets split, and the different workers will all take part in a nickel all reduce. So both runtimes are agnostic to what exactly you do within your task definition, but it's more about what they can do around that to help you enable that pattern. So besides the caching of communicators and managing of the streams, the other important bit is that Legate will make sure that tasks that are taking part in the same collective communication will execute concurrently. So they will start about the same time, and they'll to execute atomically on those GPUs. They'll continue to execute, or not atomically, but they won't be preempted. And they will also execute atomically with respect to other tasks that also want to use communicators. So that's one way that the runtime helps you avoid deadlocks. To be clear, you can launch workers in Dask as well that will do this this kind of this pattern. Like they'll start and then they'll start communicating with each other. And libraries like Dask, XGBoost, for example, would do that. But there is the default scheduler doesn't give you such a safety mechanism. But there are other features inside of Dask that might be relevant if that's what you want to do. And just as a plug, I will advertise that if this is what you need to do, if you need to build up tasks that execute a collective communication as part of their execution, then you should stay for the 10 a.m. talk to learn more about the room 230B. So. Not stay in this room 230B, excuse me. All right. So, okay, so that's that. A question that comes up often, for which I don't have an example, and I'll try and motivate why, is interoperability between the tasking runtimes. So it often comes up, why doesn't Legate and Dask kind of use them in the same program? What will go wrong? Like I already have a piece of my computation in Dask. How can I transition? Unfortunately, the answer is not satisfactory. So you have the two runtimes, and they both have a notion of a task graph, but those notions don't necessarily probably not going to compose with each other. So it's not like you can drop one runtime's graph into the other and have it execute. So the quote-unquote best you can do is you can essentially have a handoff from one to the other. So you need to have some import-export scheme so that each runtime would provide a description for where the data is, how the data is partitioned currently. You need to make sure to copy the data if the placement isn't acceptable, if the existing placement isn't acceptable. You need to transfer the data from one to their, have some borrow mechanism or something like that, so that the data can be, the ownership of the data can be moved. And you need to coordinate resource allocation, which is not a unique problem to runtimes, but any system that does its own memory management, you would need to coordinate that memory allocation, and you would need to make sure that whatever runtime goes first will clear all of its intermediate uses, so that it will pass that to the next one. So there's no standard way to do this that I'm aware of. It can be done, and we've done it, for example, to interoperate with MPI applications, but it's a pretty expensive operation, so you're not meant to do every iteration in an iterative workload, and it's typically not something that neither of these runtimes or others typically supports it, although it is an understandable question. Yeah, so I think that's the main content that I had. I will summarize what I've been trying to say, which is that these tasking runtimes are an interesting model for building up these multi-GPU applications. And the two that I've shown are representative examples, and they take a different approach to data abstraction. And you can, if you're an end user and the collections that already exist work for you, then you can be productive. The is what do these runtimes provide? What kind of support do these runtimes provide for someone that needs to go beyond the level of the basic of the existing collections? So my thesis is that the more that the runtime understands about your intern, the more it can help you. So the more that it has visibility over what your data is meant to represent, the more it can do for you, like maintaining the data structure invariance, moving data between memories, picking the partition, deciding how and when to repartition, and even ensuring deadlock safety when doing concurrent execution. All right, and that's it. So I have this slide with all of the talks in this session. So feel free to take a picture and go ahead and see what else is out there. Thank you.
I think we have some time for Q&A. Anyone have a question?
So yeah, thanks for a really clear explication of these two different programming models. The other major library that appeared in that blob in your chart was Ray. Can you say a little bit about the similarities and differences between programming models you presented and like Ray's programming model?
Yeah, I'll be honest, I'm a lot less familiar with Ray than I am with Dask. From what I understand, the basics are the same of a deferred execution model, but there's also an actor. There's a task graph model, and there's a more prominent actor execution model, and they're both kind of first-class citizens in a way. But that's about the level of understanding that I have. Yeah, from what I've heard from practitioners, they're both used. They don't necessarily jive as well with one another, but they're both supported within that model. So maybe there's others in this room that know more about Ray than I do.
Got it. Thank you.
Yeah, thank you for the great talk, Newman. I have a question about, at one point you said the Legate guarantees data coherence. Do you mean that in terms of sort of like sharing in-memory buffers without making copies, etc., avoiding memory fragmentation, and so on?
So it's more about when you have different tasks flying and they are, they're both taking read-write access over the same collection of you. There's another thing that I didn't show, which is that the dependencies don't just come from operating at the level of the full array, but you might be operating on a slice of the full array. So there needs to be an analysis in the background that understands when, based on the pieces that are being updated, there could be different versions of the array or different. You can have a piece of an array that's on a local memory because mutability is supported. You can have a piece of the array that's only partially valid. So the runtime will need to know, what task can accept this, partially updated instance, and then it also needs to, because all of this is planned ahead of time. You also need the intermediate stages being the intermediate versions being staged as the tasks are executing. So the point is that if you launch a task at the tail end, you'll always get a version, but that version might have come from part data that you had and part data that it's going to come from somewhere else, right? So that's the point. In terms of fragmentation, that's always a problem. There is a allocator, the allocator tries to fill the holes as well as it can, but that will inevitably happen.
Yeah, thank you. Follow up if possible. Yeah, so how far do you push this data coherence guarantee? Is it all the way to the level of like memory safety, where you can't mutate what you don't own, etc. Sort of like a more sort of memory ownership model, like newer languages tend to implement, or.
So in this case, the memory model that Legate assumes is pretty simple. So as long as I'm giving you the latest version of the data and I'm waiting for that transfer to be the signal to be received from whatever copy engine is doing that fill in. As long as I've received that signal, then you will get memory, and within your task, you can do whatever. If you need to do lock-free data structures or some sort of unordered memory operation, you can do that. But by default, the runtime will keep a sequential model of memory consistency.
Got it. Yeah. Thank you.
I think we have time for one more question, if any. If not, then please enter a chance to win a $50 gift card from our gear store by filling out the survey. And we, again, thank you very much. Thank you, Manolis, for that great talk.